Have you ever wondered how our vast universe came into existence? A question that has puzzled humans for eons. The most widely accepted explanation, the Big Bang Theory, offers a tantalizing glimpse into our universe's origin. This theory suggests that our universe started as an infinitesimally small, hot, and dense point, known as a singularity. Picture a dot, so small that it's virtually non-existent, yet containing everything that would eventually become our universe. This singularity was a crucible of unimaginable conditions, packed with infinite density and scorching heat. In a moment of cosmic inception, this singularity began to expand. And expand might be a bit of an understatement here. It was an explosive, faster-than-light inflation that set the stage for the creation of everything we know and everything we are yet to discover. In less than a blink of an eye, the universe inflated from a tiny singularity to an unfathomably large expanse. This rapid expansion was not just an explosion of matter and energy, but also an explosion of space and time itself. The universe was not expanding into anything. Rather, the universe was creating its own space as it grew. And within this rapidly expanding space, matter and energy began to cool down and coalesce, eventually forming the galaxies, stars, and planets that dot the cosmos. The universe as we know it today, with all its complexity and diversity, originated from that initial singularity. This process, from the singularity's expansion to the creation of matter, energy, space, and time, is what we call the Big Bang. It's a theory that tries to explain how we transitioned from nothingness to everything, from an infinitely dense point to a vast, ever-expanding universe. So from a point of infinite density, we got the vast expanse of the universe we see today. Fascinating, isn't it? But what if the universe has always existed in its current state? Let's take a detour from the Big Bang and venture into the realm of the steady-state theory. This alternative suggestion posits a universe that is timeless, unending, and consistent in its average properties over time. Quite a fascinating perspective, isn't it? The steady-state theory is like the cool, mysterious stranger at a party, an intriguing counterpoint to the more popular Big Bang theory. It was proposed in the mid-20th century by a trio of brilliant minds, Herman Bondi, Thomas Gold, and Fred Hoyle. The theory suggests that the universe is not evolving or changing over time. Instead, it maintains a constant density. How, you might ask? Well, this theory suggests that new matter is continuously created to fill the expanding universe, thus maintaining an eternal and unchanging cosmos. Imagine a universe that is like a never-ending party, where as soon as one guest leaves, another one magically appears to take their place, keeping the party going indefinitely. However, as captivating as this theory might be, it fell from grace in the late 20th century. Why? Well, the primary reason was the discovery of the cosmic microwave background radiation, or CMB. This faint whisper of light from the early universe serves as a cosmic baby photo, a snapshot of the universe just a few 100,000 years after the Big Bang. The existence of the CMB was a prediction of the Big Bang theory, which the steady-state theory couldn't account for. Moreover, observations of distant galaxies also showed that the universe was not unchanging but evolving over time. These galaxies looked different from nearby ones, indicating that the universe had changed over billions of years. The steady-state theory, with its claim of an unchanging universe, couldn't explain these observations. And so, despite its unique perspective and the elegance of its concept, the steady-state theory found itself overshadowed by the empirical evidence supporting the Big Bang. It's a testament to the scientific process where theories must stand up to the rigorous test of evidence. Despite its elegance, the steady-state theory couldn't stand up to the test of evidence. Scene script. Or could the universe be like a phoenix, continuously dying and being reborn? Enter the oscillating universe theory. This intriguing idea proposes that our universe is just one of an infinite series of universes, each born from the fiery ashes of its predecessor. Like a cosmic accordion, the universe expands and contracts, oscillating between big bangs and big crunches in an eternal dance of creation and destruction. Picture it. A big bang occurs, birthing a universe that expands over billions of years. Then, as if tugged by an invisible string, it begins to slow down, stop, and reverse. Everything that was once scattered across the cosmos starts to pull back together, culminating in a big crunch. This unimaginable event is not an end, but a new beginning. The energy and matter compressed in the crunch ignite another big bang, and the cycle begins anew. Each of these cycles births a new universe, distinct and separate from the last. There are no remnants, no echoes of the past. Each universe is a blank slate, with no memory of its predecessor, like a phoenix rising fresh and new from its own ashes. But as poetic as it may sound, the oscillating universe theory faces significant challenges. The biggest one? There's no concrete evidence for a big crunch. Our current observations show the universe is not just expanding, but accelerating in its expansion. If this trend continues, there won't be a big crunch. Instead, the universe will keep expanding until it grows cold and dark. Moreover, to oscillate, the universe needs to have a specific amount of matter, enough to slow down the expansion and reverse it. But according to current cosmological data, we simply don't have enough mass for that to happen. While beautiful in concept, the oscillating universe theory is yet to find solid footing in evidence. Yet it remains a captivating idea, a testament to the human imagination and our ceaseless quest to understand the cosmos. The universe, forever dying and being reborn, each cycle a new stage for the grand play of existence. But what about the end of the universe? How will it all wrap up? Now that's a question that has captured the imagination of many. The most accepted theory about the universe's end is known as the heat-death theory. Let's dive into it. Imagine a cup of hot coffee in a chilly room. Over time, the heat from the coffee disperses into the room until there's no difference in temperature between the two. The coffee cools down, the room warms up, and equilibrium is achieved. This is a simple example of entropy, a principle that governs the universe. Entropy, in the most basic terms, is a measure of disorder or randomness. In a closed system like our universe, entropy tends to increase over time. This is the second law of thermodynamics, and it's as fundamental to our understanding of the universe as gravity. So what does this have to do with the end of the universe? Well, the heat-death theory posits that the universe, like our cup of coffee, will eventually reach a state of maximum entropy. At this point, all the energy in the universe will be evenly distributed, and no work can be done. The stars will burn out, galaxies will drift apart, and eventually, even the smallest particles will cease to move. The universe will be dark, cold, and lifeless. There will be no heat, no light, and no life. This is the heat death of the universe. This might sound bleak, and well, it is. But remember, this is billions upon billions of years in the future. For now, the universe is alive and vibrant, filled with stars, galaxies, and potentially, life beyond our own planet. The heat-death theory is a reminder of the impermanence of everything, even the universe itself. It's a testament to the ever-changing nature of existence and the inexorable march of time. It's a chilling thought, the universe ending not with a bang, but with a whimper. But it's also a call to appreciate the beauty and wonder of the universe while we can. Because in the grand cosmic timeline, our existence is but a fleeting moment. Or could the universe's end be more dramatic, ripped apart by its own expansion? Picture this, a theory so dramatic. It suggests that the universe, in its ceaseless quest for expansion, could ultimately tear itself apart. This, my friends, is the essence of the Big Rip theory. The Big Rip theory is a cosmological model that describes a possible fate of the universe, a fate quite unlike any we've discussed so far. It postulates that the constant acceleration of the universe's expansion, driven by a form of dark energy, could escalate to such an extent that it literally rips the universe apart. This isn't a gentle, fading away into the night. No, this is the universe tearing at the seams, a catastrophic end to everything we know. The consequences of such an event would be unimaginable. This theory suggests that first, galaxies would be torn asunder, their stars flung into the vast void of space. As the acceleration continues unchecked, the stars themselves would be next, ripped apart, their planets cast adrift. With nowhere to go, these now rogue planets would meet the same fate, torn apart by the relentless expansion of the universe. But it doesn't stop there. As the universe's expansion continues to accelerate, even atoms, the fundamental building blocks of matter, could be torn asunder. Imagine that the very fabric of reality, the smallest particles that make up everything we see, touch, and experience, ripped apart by the universe's insatiable expansion. But before you start worrying, let's put this into perspective. If the Big Rip theory holds true, it's not something we need to worry about for a good while yet. We're talking billions of years into the future, so there's no need to cancel your weekend plans just yet. Whether it's a heat death or a big rip, the end of the universe is a long way off, but the exploration of these theories gives us a deeper understanding of the cosmos we're part of.